Welcome to the deep dive. Today, we're looking at advanced optics, pulling out some really foundational breakthroughs from the sources you've given us. We want the surprising stuff, the elegant insights.
Exactly. We're aiming to go beyond just, mirrors and lenses. We're diving into the core physics, things like how we know the speed limit of the universe and even how we measure stars.
Okay, so let's start at the beginning, really. James Clerk Maxwell, his equations describe light propagation completely, right?
They do. It's the bedrock. But the real wow moment, I think, was predicting the speed of light itself.
How did that come about? It wasn't directly from studying light, was it?
No, not initially. He derived the wave equation from his work on electricity and magnetism, and he found the speed of these electromagnetic waves depended on two constants.
Constants from electrostatics.
Yeah, the permittivity and permeability of free space, epsilon dollars and another dollars. Things scientists already kind of knew from lab experiments with charges and currents.
So wait, they had these numbers from like capacitors and inductors.
Basically, yes. And when Maxwell, or others shortly after, calculated $1 C Solar, they got about $2.99 times 181 meters per second, which was remarkably the measured speed of light.
That's incredible. So light is an electromagnetic wave, just like that.
Just like that. It unified optics and electromagnetism, a true physics mic drop moment, as you might say.
Okay, so that's light in a vacuum, speeds. But light rarely stays in a vacuum. What happens when it hits, say, glass or water?
Right, enters matter, then things get more complicated, speed changes, and crucially, it changes depending on the light's frequency, its color.
That's dispersion, isn't it? Like a prism splitting white light.
Exactly. The index of refraction 9-Aller isn't just a single number anymore. It depends on frequency, not on omega. Macroscopically, the light interacts with the material as a whole.
And the sources mention the Lorentz model to help picture this.
Yeah, it's a classical model, but useful. Think of electrons in the material as being on tiny springs. The incoming light wave pushes them, makes them oscillate.
Okay, simple enough.
But if the light's frequency gets close to the natural frequency of those electron springs, the material's resonance things get weird. You get what's called anomalous dispersion.
Anomalous, meaning unexpected.
Very unexpected. In that specific frequency range, near resonance, the math shows the index of refraction, Nollar, can actually drop below 1.
Hold on, Nollar's less than 1. But the speed in the medium is phi dollars, and Lollar is then phi is greater than c dollars.
That's the apparent paradox. The phase velocity, phi p10, seems to exceed the speed of light. It looks like we've broken relativity.
So did we? Can light actually travel faster than light in a medium?
Well, this is where you have to be really careful about what speed means. Does phase velocity carry information?
I guess not. A pure single frequency wave goes on forever, right? No start, no end, no message?
Exactly. A perfect infinite sine wave is a theoretical idea. It can't carry a signal. To send information, like a pulse of light, you need a wave packet.
A mix of frequencies?
A mix of slightly different frequencies, yeah. And that packet, the envelope of the wave, travels at the group velocity, Doppler.
Yeah. Okay. So the signal travels at $5, not $5.
Correct. And the key is, even in these strange anomalous dispersion regions where VPAC revers, the group velocity, $5, the speed the actual information travels at always stays less than or equal to.
So relativity is safe. The universe's speed limit holds.
It holds. No faster than light communication possible this way. It's a subtle but absolutely critical distinction in optics.
That makes sense. It's about what actually carries the signal. Okay, so we've tackled speed. Let's shift gears to manipulating light. How about polarization? Can we use reflection to control it?
Definitely. When unpolarized light hits a surface, like glass, the reflection treats the different polarization components differently.
You mean light waves oscillating in different directions relative to the surface?
Precisely. We usually talk about polarization, parallel to the plane of incidence, and Hughes polarization, perpendicular to it. They reflect with different efficiencies.
And there's a special angle.
There is. It's called the Brewster angle, phi to b beer. If unpolarized light comes in at exactly this angle, the reflected light is only spolarized. The p-polarized light is completely transmitted. None is reflected.
So you get perfectly polarized light just by reflecting it. How do you find that angle?
It's surprisingly simple. The tangent of the Brewster angle is just the ratio of the refractive indices of the two materials, 30 on 1 waltz.
Okay, so for air to glass, 2A is about 1.5. A pan dollars is 1.5.
Right, and the angle set at B12 works out to about 56.3 degrees for typical glass.
Is this used in practice?
Oh, absolutely. Lasers often have Brewster windows inside the cavity. These are transparent plates tilted at the Brewster angle.
Why?
because light bouncing back and forth inside the laser cavity passes through these windows. Only one polarization state experiences no reflection loss at the window surfaces. So the laser naturally ends up emitting light with that specific polarization. Very clever.
Elegant, using geometry to purify the light. Okay, another way to control reflection is with thin films. Anti-reflection coatings, AR coatings, we see them everywhere.
Yes, on glasses, camera lenses, solar cells, they're based on interference.
Making reflected waves cancel each other out.
Exactly. Destructive interference. To get perfect cancellation, zero reflection, you need two conditions met.
Condition 1.
Thickness. The film needs to be exactly 1/4 of a wavelength thick. But critically, that's the wavelength inside the film material itself, which depends on its refractive index, Onondel 1.
Okay.
So $T equals lambda, 4n11.
Okay, quarter wave thickness, condition 2.
This one's about the materials. The refractive index of the film on dollars met has to be the geometric mean of the indices of the medium the light comes from, $2, and the substrate it's coating, NS.
Geometric mean. So $112 equals NS sees all.
That's the one.
So let's say I'm coating glass, 1S, this is $1.555. Starting from air, and as Abiel 1.0 times 1.5.
Which is quartered $1 is about $1.22.
Right. So you need a material with that specific index, and you need to deposit it with precisely quarter wave thickness for the target wavelength.
Exactly. It's quite demanding to get really good AR performance, especially over a range of colors. That simple index condition really restricts your material choices.
Fascinating how these simple mathematical relationships dictate complex engineering. Okay, let's shift perspective again. We've talked propagation, manipulation. What about the inherent structure of light? Coherence.
Right. Coherence is all about correlation.
Yeah.
How related is the light wave at one point in space or time to another point?
How do we measure that?
Well, the complex degree of coherence, gamma, quantifies it. And for the kind of light we usually deal with, quasi-monochromatic light, its magnitude, gamma, is directly related to how clear the fringes are in an interference experiment.
Like in a Michelson interferometer. If you get sharp, high-contrast fringes, the light is highly coherent.
Precisely. High gamma means high visibility fringes. Low coherence, like from a light bulb, gives washed out or no fringes.
Okay, that's temporal coherence, correlation in time.
Okay.
What about spatial coherence? The sources bring up something called the van Sittert-Zernike theorem. Sounds complex.
It sounds complex, but the idea is incredibly powerful. It connects the spatial coherence of light, measured far away from a source, like starlight reaching Earth, to the physical size and shape of that source.
How?
The theorem states that the mutual coherence function, which describes the spatial correlation, is essentially the Fourier transform of the intensity distribution of the source itself.
Wait, the coherence pattern is the Fourier transform of the object. So if we measure the coherence...
You can do an inverse Fourier transform and reconstruct the image of the source, or at least its size and brightness profile.
So we can measure how correlated the light is between two telescopes spaced apart on Earth.
Yes, measure the coherence for different separations.
And figure out the actual size of a distant star.
Exactly. It's a cornerstone of stellar interferometry. Instead of building one impossibly huge telescope, you use coherence measurements between smaller ones to get equivalent resolution. It lets us measure the diameters of stars.
That's mind-blowing. Remote sensing on a cosmic scale using correlations. But don't these interference measurements, phase measurements, suffer terribly from atmospheric turbulence?
They do. Hugely. Keeping things stable to within a fraction of a wavelength is incredibly hard through the atmosphere. That difficulty spurred a different approach.
Which was?
The Hambury, Brown, and Twist experiment. They decided, essentially, to forget about phase.
Forget about phase. What's left?
Intensity. Amplitude. They measured intensity correlations. They looked at how the brightness fluctuations measured at two separate detectors were correlated.
How does correlating brightness help?
It turns out that intensity fluctuations also contain information about the source size, due to the quantum nature of light, actually. But the crucial advantage is that intensity correlations are much, much less sensitive to phase shifts caused by the atmosphere of vibrations.
Ah, so it's a more robust measurement in real-world conditions.
Way more robust. It allowed them to make groundbreaking measurements of stellar diameters that were impossible with phase-sensitive interferometers at the time. A really clever workaround.
Finding a signal that ignores the noise. Brilliant. Okay, we've covered a lot. Propagation, speed limits, manipulation with angles and films, structure via coherence. But almost all of this assumes something fundamental.
Linearity.
Linearity, the principle of superposition. that light waves pass through each other unchanged, that one wave doesn't affect another.
Yes, that's the basis of standard optics. But for the final thought, what if that principle breaks down?
And break down.
Oh, yes. Welcome to the world of nonlinear optics.
Nonlinear, meaning superposition, fails.
Completely fails. In certain materials, especially when the light intensity gets very high, the material's response is no longer just proportional to the electric field of the light waves.
So the material doesn't just passively let the wave through?
No. The polarization, math BFP8, induced in the material starts depending on the square or the cube, or even higher powers of the electric field. Math BFP isn't just linear in math BF anymore.
And what does that do?
It means light waves can interact, they can mix, they can change each other's properties. The light fundamentally alters the medium, which in turn alters the light.
Okay, that sounds profound. What's a major application of this?
Probably the most common is frequency conversion, specifically second harmonic generation, or SHG.
Generating the second harmonic,
Yeah,
doubling the frequency.
exactly. You send intense light of one frequency into a nonlinear crystal, and out comes some light at twice that frequency, so half the original wavelength.
Like changing the color of light?
Precisely. It's how we get green laser pointers, for example. Many of them start with an infrared laser diode, maybe around 1064 nanometers. That infrared light goes into a nonlinear crystal
When the nonlinearity mixes two infrared photons.
to create one green photon at 532 nanometers. It's routine technology now, all thanks to breaking the superposition principle.
So just by cranking up the power, we force light to interact with itself and create new light. That's a fantastic twist on basic optics.
Thank you. This has been a really illuminating deep dive.
It was my pleasure. There's so much depth there. And for you, our listener, here's that final thought to ponder. We learned that phase velocity can exceed 270 Lurs, but it carries no information because it represents an ideal infinite wave. Only the group velocity of a real finite wave packet carries the signal and respects the speed limit. What other perfect theoretical constructs exist in physics that define limits or boundaries, but maybe don't represent something physically achievable in its purest form? Something to think about.